In this video, we like to discuss the details of uniform circular motion. When we talk uniform, you might think of things like a soldier's uniform, a band uniform, a police uniform, or maybe even a sports uniform. When we talk about uniform circular motion, though, we talk about the idea of uniform meaning the same. And in this case, we're talking about things that are traveling at the same speed. And circular motion just means that the object is traveling in a circular path. We want to start by looking at the statement here and deciding if this is true or false. An object moving in a circular path at constant speed is accelerating. To answer this question, we first have to think about what the definition of acceleration is. We know that acceleration is a change in blank over some amount of time. Well, acceleration is a change in velocity over some amount of time. You can change your velocity by doing one of two things. You could change your speed or your direction. We've talked about changing speed. We do acceleration equals delta v over delta t, and you're getting faster or slower to accelerate. But we haven't talked about changing direction yet, so that's the idea of what we're going to talk about today. So what we're going to do in this lesson is talk about how can you find the acceleration of an object that has constant speed but is moving in a circle. Let's look at the example of a car traveling in a circle at constant speed, and we want to know what the acceleration is. So let's say that speed maybe is 30 meters per second, and we want to know the acceleration. Well, that's delta v over delta t, which is v final minus v initial over the change in time. But if we do this, we get 30 minus 30 over our time, which is 0 meters per second squared. And that equation then doesn't seem to work because we know that we're changing our direction, so we're accelerating, but this gives us an acceleration of 0. The reason why is we've overlooked something. Velocity is a vector, which means the direction matters. So if you think about it, if we're at the top of the circle here, we have a velocity in that direction, and we'll call that v initial. And maybe later on, we're down here, and we have a velocity in that direction, and we call that v final. Well, the problem before was that we got the change in velocity to equal 0 because we just looked at the numbers. But if we look at these vectors, remember that change is always final minus initial. Well, v final points like this, and v initial, remember if we add v initial, it goes in this direction. But we don't want to add that, we actually want to subtract it, which, remember, subtracting is just adding the opposite. So minus v initial will be in this direction. And that leaves this piece here as delta v, our change in velocity. And there actually is something there. It's not equal to 0 if we just look at the numbers. Well, how do we find out what that delta v piece is? Well, we can do that by taking a look over at our circle over here as well. So we have a triangle here, and each one of these from the center to the edge is radius. And we have this angle here, and that's actually congruent to this angle over here. And then we have this piece that we can come across like this. And since that is where the object started and where it ended, the straight line from where an object starts to where it ends is known as delta x. If we look at these two triangles, we can see that they each have congruent legs, or legs that are equal and an angle in between. So they're isosceles triangles with the same angle. So they're actually similar triangles. So we know that triangle, and we'll call this over here, v final, v initial, delta v, is similar to triangle over here, r, delta x. And remember what we're looking for is the acceleration. Remember, acceleration is equal to delta v over delta t. And our problem before is doing delta v with just the numbers, we got 0. So we got to look at this a different way. So we need to look at what this delta v is. So what I can do is I can set up a proportion comparing these similar triangles. So I can say that delta v over delta x, and that's base of one over the base of the other, is equal to v final, which we'll just call v, over one of the legs over here, which is r. Or we can say that delta v is equal to v delta x over r. And we can substitute that in for delta v over here. So that leaves us with v delta x over r. That's our delta v, and we have a delta t. And we want to clean this up a little bit. We have this delta x over delta t piece. And what is delta x over delta t? Well, remember, that's the definition of velocity. Velocity is delta x over delta t. So that's another v. So what we get from all this is that the acceleration when you're going around a circle is v times v over r, or v squared over r. And that's what we're going to use to solve for the acceleration in these problems. So let's just do a quick sample problem of this, and what we're going to do is let's get some area to work. And we have a problem here. It says that a car is moving at 20 meters per second around a turn with a radius of 40 meters. So let's use our newly developed equation. Centripetal acceleration, again, acceleration going around a circle, is v squared over r. And the velocity in this problem is 20. So that's 20 squared over 40, which is 400 over 40. Or the acceleration of this car would be 10 meters per second squared. So in conclusion, the acceleration when you're going in a circle can be found by doing the velocity of the object squared divided by the radius of the turn. And again, with this, you could solve this many different ways. Maybe the acceleration and the radius is given, and you can find the velocity. Or maybe the acceleration and the velocity is given, and we could find the radius. Or as it's stated, maybe we want the acceleration, so we do v squared over r. If you think about this equation, it should make sense, because the faster you go as you're going around a circle, you have more velocity in one direction, and then you have more velocity in the other direction. So it's a bigger change just because you have more of a change of going one way to the other way, so you get more acceleration. So that's v shows up in the numerator because of that. Also, the faster you go, the quicker you get turned around, so the less time it takes to make that change. So v also shows up in the numerator. And then when you think about the radius, if you have a smaller radius of a circle, you can get turned around quicker. So that's why r shows up in the denominator. So that kind of explains why v shows up twice. If you're going faster, it's going to be a bigger change just because you have a greater velocity to turn from one direction to the other. It also means you can turn around quicker, which results in a bigger change. And a smaller radius, so the radius is inversely proportional, allows you to get turned around quicker.